Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for November 13th, 2013.
On today's show, an array pushes solar deep into buildings, a special camera detects tumors, and a fiber optic switch is controlled by a single atom.
A new technology developed at the University of Cincinnati and called Smart Light involves a narrow grid of tiny electrofluidic cells self-powered by embedded photovoltaics and applied near the top of a window. These open-air ducts help sunlight illuminate windowless rooms deep inside office buildings. The grid can be applied to any building, residential or commercial, and the excess energy can be harnessed, stored, and directed to other applications. Today's photovoltaic cells aren't very efficient because a typical PV array loses most of the energy it's gathered in converting it into electricity. But with Smart Light, the sunlight channeled through the system stays and is used in its original form. Plans call for Smart Light to be controlled via a mobile app. It could even use geolocation data from the app to respond when a user enters or leaves a room, or simply changes seats by manipulating Wi-Fi enabled light fixtures, the researchers say. Much of the science and technology required to make Smart Light commercially viable already exists, and the researchers have begun evaluating materials and advanced manufacturing methods, but need sufficient funding to create a large-scale prototype to attract government or industry partners. A paper on the work was presented recently at an international energy forum in Italy.
People with cancer obviously have the greatest chance of survival if tumors are completely removed, but tiny clusters of cancer cells are often difficult for surgeons to recognize and remove. And doctors have to depend solely on what they see when excising tumors. But a new camera system can help visualize even the smallest, easiest to overlook malignancies. The camera can display fluorescent molecules that paint the cancer tissue. These are injected into the bloodstream before the operation, and they selectively attach themselves onto the tumor. If the corresponding area is then illuminated with a specific wavelength of light, the malignant tissue glows green, blue, red, or some other color depending on the injected dye, while the healthy tissue appears the same. This lets surgeons see clusters of tumor cells invisible to the naked eye. Researchers at the Fraunhofer Project Group for Automation in Medicine and Biotechnology developed the multispectral fluorescence camera system, which is unique in that it can display several fluorescent dyes and the reflectance image simultaneously in real time and even at very low light intensities. One advantage of the system is that delicate nerves and major arteries are also affected by the dye and can be more easily avoided during surgery. The team envisions the camera being integrated into medical imaging systems such as surgical microscopes and endoscopes. It can be converted to other combinations of dyes, and one preparation already available is used especially for glioblastomas, one of the most frequent malignant brain tumors in adults. Once the system is approved for human trials, the first clinical tests on brain tumor patients will begin. They're expected to happen in 2014. A prototype will make its debut later this month at the Medica Trade Fair in Dusseldorf in the joint Fraunhofer booth.
Fiber optic switches play a vital role in optical communication networks, enabling optical signals to be rerouted to different fiber output ports. Making these switches small enough to manipulate light would enable quantum information and communication technology. A new demonstration of such a switch shows that a single atom can direct light from one fiber optic cable to another. While a number of recent experiments have demonstrated strong coupling of single atoms and solid-state quantum emitters to whispering gallery mode microresonators, a team at the Vienna University of Technology say that their method is unique because it uses a novel type of silica WGM known as a bottle resonator. The Vienna team's bottle resonator is conceptually similar to other WGM microresonators, but has the advantage of being fully tunable. They say they can make 100% of the light from the glass fiber go into the bottle resonator, and from there it can move on to a second glass fiber. Unlike a standard light switch, which is either on or off, a quantum switch can be both on and off at the same time, making these switches powerful tools for quantum information processing. Next, the scientists plan to exploit the fact that a rubidium atom can occupy different quantum states, only one of which interacts with the resonator. This will allow them to explore properties of quantum mechanics without needing exotic machinery found only in labs, and instead using commercially available glass fiber cables. A paper on the work appears in Physical Review Letters.
Well, that's it for this edition of Light Matters, the Photonics Industry's only weekly newscast.
As always, you can write to us with your questions or comments at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.